Hello, this video is entitled The Cross Product of Two Vectors. Now in my video dot product, I mentioned that there are two types of multiplication of vectors that yield two completely different results. One's called the dot product. This one is now called the cross product. Now the dot product always yielded a scalar, a numerical answer. A cross product is going to yield a vector answer. So let's take a look at how we get this cross product. And it's a matter of using this formula right here. So you have two vectors u and v. So the dot symbol is for dot product, and the x symbol that you use for multiplication sometimes is now the cross product notation. So we do this as, so you have these three components, u1, u2, u3, v1, v2, v3. And it goes u2, v3 minus u3, v2, comma, the next component of the cross product will be u3, v1 minus u1, v3, and then u1, v2 minus u2, v1. Now, from a graphical visual standpoint, the cross product gives us kind of an interesting result. Is the cross product is going to give you a vector that's orthogonal to both u and v. So in other words, then that if you did the dot product, you do your cross product and then you dot product with both vectors, it should be 0. Now this idea kind of only applies to space vectors. It wouldn't make much sense in the plane. For dot products, you can do it in the plane or space. But this one would not make any sense in the plane. You couldn't really get a orthogonal vector sticking up out of the xy plane. Now we're going to cross product these two vectors. U cross v. And u is given as I plus 6j. So you might be thinking, hey, there's not a third component there. Are you sure this is not a... Yeah, it's definitely going to be a plane result. So no problem. If you don't see a k there, just add a 0. So I plus 6j would be the same thing as the vector 1, 6, 0. And here we have negative 2i plus j plus k makes it negative 2, 1, 1. So to follow the cross product formula from above, let's see if I can actually... Well, okay, I'm using that formula up there even though it's not visible right here, so I'll walk you through it. So first one is u2 times v3. So 6 times 1 makes 6 minus u3 v2. 0 times 1 is 0, so you have 6 minus 0. The next one is u3 v1. 0 times negative 2 is 0, minus u1 v3, which is 1 times 1. The last one, u1 v2, 1 times 1, minus u2 v1, 6 times negative 2, negative 12, so you have 1 minus a minus 12. So your cross product result will be 6, negative 1, 13. Now, just for the heck of it, not saying this next step is mandatory, but I did take this cross product result and I dot product with both of the original two vectors. Right here, and got 0. I was just checking that the cross product is correct because, to be correct, it would have to dot product with both your original vectors and be 0. And I just put it in the Maple software just for the heck of it and Maple got what we got. So let's take a look at some of these properties. U cross V equals the negative of V cross U. So the only thing that would happen if you reverse the two vectors when you cross product, it will give you the negative of your previous result. So that means back up here, we just did U cross V, so had another part of this question then asked what's V cross U. We would not have to actually make that calculation because it would just be the negative of this one. In other words, V cross U would automatically be -6, +1, -13. Now, as mentioned with the dot product, you have some properties here that you don't have to necessarily use. This says if you take U and you do a cross product with V plus W, it's the same thing as U cross V plus U cross W. But I wouldn't even use that property. If I had to perform number 2 command there, that rule, I would just add V and W first and only do one cross product. So just because that property is true, it doesn't mean you have to solve it that way. Here's one with a scalar multiple. Any vector cross product with a 0 vector would give you the 0 vector. U cross U, any vector crossed with itself would be the 0 vector. In fact, well, I'll come over the other side and go into more detail about that. And then this one's just kind of reordering it. Okay, no big deal. U dot V cross W would be the same thing as U cross V dot W. So here's some geometric properties. U cross V is orthogonal to both U and V. The magnitude of U cross V equals the magnitude of U times the magnitude of V times sine of theta. U cross V equals 0 vector if and only if U and V are scalar multiples of each other. So that's really just an extension of rule number 5 over here. You cross U with any parallel multiple of itself, it's going to be the 0 vector, meaning it doesn't really have an answer. Because if you take two vectors that are parallel, and let's say you map them on top of each other, which obviously parallel vectors can do. See if I can sort of explain this very well this way. You got those two vectors. Well, if you think about this and think about it being in space, that you can draw theoretically infinite perpendicular orthogonal. Well, say that's a terrible drawing, but theoretically, you think about this in space, you can have lots of 90-degree answers to that vector over and over and over. So that's why it wouldn't have an answer, because it's like infinite answers, meaning it doesn't have an answer. So parallel vectors would have a cross product of 0 vector. 0 vector, very important. That's not like the same as saying, two orthogonal vectors have a dot product of the number 0. Okay, I'm going to skip the mechanics on this one, but this one I just brought in to show you that property 3 with a numerical example. And I took two vectors. You see that one V is a multiple of U. It's -2 times U. And I did the cross product formula, and look what I got. I got 0, 0, 0, the 0 vector. And I'll run to the cross product real quick here. And then usually students, once they see it a couple times, I'm not going to do all these cross products. Well, these are the vectors, but once they see how the formula operates, and then you practice it yourself, it's not too bad. A little more involved, obviously, than it's not as simplistic as the dot product, but I always provide that formula for my student, or they can use it on their formula sheet if I'm allowing formula sheets. Sometimes I give formulas. It depends on how I'm conducting it for that semester. But my class, either way, whether you're writing it down on a piece of paper or I'm giving it to you, you would not have to memorize the cross product formula. So we have U2 V3, negative 1 times negative 6 would be positive 6. U3 V2, 3 times 2 is positive 6. I have V3 U1, negative 6 times 2 is negative 12. I have U1 V3, U3 V1, 3 times negative 4 makes that negative 12. Then the last one I have U1 V2, 2 times 2 is 4, and then U2 V1 is negative 1 and negative 4, and then they're all the same, so they subtract and it'd be 0. Let me check and see. I think I forgot to mention this property we're about to use right now. I got so distracted they're talking about, focused on this whole idea about the parallel vectors. I forgot number 4, that if you take, if U and V are adjacent sides of a parallelogram, the area of that parallelogram is the magnitude of U cross V. So if you're doing a triangle, it would just be half of that. So let's see if I can sort of draw a picture here. It won't look very good, obviously, without using a stylus, but so I'll take 2 vectors like this. And then, so that's the U and V, the order doesn't matter. So now I'm going to just kind of dot it out here a little bit to make it form a parallelogram. Anyway, come down here. And then so if you want the purple one to be U and the blue one to be V, that's fine. Cross product, magnitude, that would be the area. And then if it were to ask what's the triangle, the area of the triangle formed by those vectors, like so, that it would just be half of this formula, because that parallelogram would be 2 equal triangles put together. So that's what the next example is about to focus on. Now we did this before in the section on parallel, determining whether it was a parallelogram. So that we've done before on the space coordinates section. So I've already done an example of this where I explained that all you have to do is verify that you have 2 sets of parallel vectors, then you're guaranteed it's a parallelogram. Because if you go back to look at that section, whether you watch the video or just look at the notes, there's 6 vectors between those 4 points. 2 of them are going to be the diagonals. But if it's a parallelogram, they're going to be 2 parallel vectors that form the sides of the parallelogram. So I formed all 6 vectors, and you see the 2 green check marks. Remember, they just have to be multiples of each other to be parallel. They don't have to be exactly the same. But AB and CD are just off by a multiple of -1. That just means they go the opposite direction. And then AD and BC are exactly equal to each other. So the 2 green check marks mean those are parallel. The 2 purple check marks means those 2 are parallel. So we guarantee we have a parallelogram. So all I have to do is take one of the green vectors and cross it with one of the purple vectors. It doesn't really matter whether opposite direction. Those would be the adjacent vectors. And then we completely ignore the diagonals. So you see, I just chose these 2 right here, A, B, and BC. All right, so I'll skip the walkthrough on the cross product again, but there I brought the formula down for you to see. And I mentioned that it's AB cross BC. And I got the vector 18, -14, -20. One thing we learned back earlier in vectors is that we can take a scalar multiple out, positive scalar multiple out if we want to. So I pulled a 2 out of here. So pulled a 2, and then that would leave 9, -7, -10. Just makes it a smaller, magnitude you have to calculate. So 9 squared is 81, 7 squared is 49, and then 10 squared is 100. And I have 81 plus 49 plus 100 is 230. And then I mentioned this earlier, here, the 1/2 of that, mentioned this about would form the triangle. So it's half of that. So the area of that parallelogram would be 2 times the square root of 230. So here it's just given a triangle. Now, since we could have done it with 4 points of the parallelogram, but with a triangle where it's just given 3 points, just find any two vectors out of the 3. We're not looking for specifically parallel here, although we could have done it with the parallelogram also. So I just found 2 vectors, AB and AC, crossed them, and I'll take the magnitude of that. I pulled out a common 2 here. Took out the magnitude, so the area of that triangle formed by those 3 points would be 2 times the square root of 11. I'm sorry, square root of 11, excuse me. Because the magnitude of the cross product is 2 square root of 11, and the area will be half of that. So it'll just be square root of 11. And let's see. Looks like I took this is from problem in section 11.2, so evidently, okay, I use these same numbers. Well, I didn't use my color coding on my check marks this time, did I? Got a little sloppy with that. But anyway, let's see if I can do these again. With the green and the purple. Not that you probably needed me to do it, but might as well stay consistent. So I'll do this one as the green that pairs up with this one. And not that it mattered, I even graphed this result in maple. So that purple check mark means that this pairs up with that one. And there we have it. Alright, so there's actually a picture of it. Not that we needed it. So I took the 2 vectors, same thing, cross product. And kind of some big numbers there. So kind of a weird answer. Square root of 37, 41. So it's numerically it's a little over 60. And here's all the maple commands. Norm is a common term to use to find magnitude. You find the norm of something, so that's what maple even recognizes it as its command. So versus normal, but norm and magnitude are kind of the same thing. All right, so you see I did the cross product and then did the norm, which is the magnitude of that. Now we have something called the triple scalar product. We can use this. You got to say you got 3 vectors. Don't worry about this determinant notation. I skipped over that. The cross products actually developed from using the determinant idea in linear algebra. I just skipped that idea and just kind of went straight to the formula without having to use it. But because I wasn't assuming that everybody was familiar with determinants, it was easier just to go straight to the formula. Same thing here. Now what we're going to use this triple scalar product for here is you can use it to find the volume of what's called a parallelepiped. I can't pronounce it. But anyway, if you took a parallelogram and then turned it into a 3D shape. Sort of like a rectangular solid, but it's not a rectangle. It's a parallel. Well, all rectangles are parallelograms, but not all parallelograms are rectangles. So it's a solid that looks like this. But the interesting thing about this formula is, so it has the absolute value, because obviously this is a volume measurement, so it has to be positive. Depending on what order that you do this triple scalar product, you might get a negative or a positive result. But the absolute value takes care of this. What's interesting is if you do U dot V cross W, you can put the vectors in any order there and it won't matter, meaning that, but now sometimes you'll get negative answers, sometimes you'll get positive, but the whole idea is the absolute value takes care of that. So basically you just take any two of your three given vectors and then get that cross product, cross them, and then dot it with the other vector, and that's it, in any order. It's kind of weird how that works. I think I did a couple of orders here. Yeah, I did a couple of orders, and I got the same, negative 72, which turned out to be positive 72. And I'm sure some of the other orders would give you positive 72. Anyway, so here are your three vectors. No drawing required. So the first way I followed the formula exactly. I did V cross W, and then I'll dot it with U. So V cross W equals negative 24, negative 24, 24. And then take U and dot it with that result. So 131 dotted with that vector, negative 24, negative 24, 24, gives you negative 72. That means the volume of that parallel pipe is the absolute value of negative 72, so it makes it a volume of 72. So I was just showing, I reversed one of the orders. Now right below, before I reverse the order, I have the maple. So there's how the maple did it. It did the dot product with that cross product to get the same negative 72 that I got right there. But here I said, what if, instead of going U dot V cross W, I said, what if we go V dot U cross W? So I take U cross product W, negative 12, 0, negative 12, and then I dot it with U, which is 0, 6, 6, negative 12, 0, negative 12. I got negative 72. Absolute value of that is positive 72. So it did not matter. Maybe you think that's a coincidence. That's okay. If you want to try another order if you'd like, but there's no need to. But that was not a fluke that they both eat. But like I was saying though, if you do another order, you might actually get positive 72. So the absolute value of positive 72, of course, will still be 72. So either way, you got it. So all right, that concludes this video on cross product.